some work with comparing functions. And some of the terminology is a little bit different, so you'll see some words up here with definitions in red. Write those down. Have those words written down. We will make some connections between things we already know and things that you might be seeing for the first time today. So here is the situation that we're going to use. Felicia decides to track the snowfall. There are already 2 inches of snow on the ground from a previous storm. Felicia measures the snow from today's storm at the end of every hour. She found that exactly 1.5 inches of snow fell each hour. If it snowed at this rate for 5 hours, how much snow is on the ground at the end of every hour? Complete the table and write an equation. So this represents a function, because every hour we're going to have a snow amount. It's not like in hour 2 I can have 2 inches and 5 inches, right? I have one value. When we were identifying if something was a function or not last week, we had the conversation that as we shift into this week, everything you see really for this topic will be a function, because now we're going to start to compare them. So we'll go over the parts of a function that we can compare. So let's fill in this table. At 1 hour, how much snow will be on the ground? Why 3.5 and not 1.5?
Because we have 2 before the other storm even started.
Exactly. Before this storm even started, I had 2 inches on the ground. So yes, 1.5 inches fell in the first hour, but that was added on to what was already there. So I have 3.5. How about hour 2? 5 inches. How about hour 3? How much snow after hour 3? 6.5. 6.5. Good. How about hour 4? 8 inches. And how about hour 5? 9.5. 9.5. So what's happening every hour? Our snowfall is increasing by 1.5. Good. Now, if I wanted to write an equation to represent this scenario, what values would I utilize? What can I replace in this equation with a value that I know? Excuse me.
For your,
Laura, go ahead.
Oh, so for the y-intercept part, like the b, you can replace that with 2.
Why can we replace that with a 2? What does this mean, that value for 2? Or that value of 2, I should say.
0 is x.
If x is 0, y would be 2. What does that mean in the context of this problem?
That with no time you get.
With today's storm, if it snows not at all, there's still going to be 2 inches of snow.
So before, at the time of 0, when no hours have passed, we have 2 inches of snow on the ground. What other value can I replace here? The m. And what am I going to replace the m with?
1.5.
1.5, because that represents what?
Per hour.
How much snow per hour? So this is the rate that's changing every hour, and this is the value that we're starting with. So we're going to work with some different types of terminology. We're familiar with proportional relationships that start at 0, 0, such as 0 hours worked and $0 earned, right? If I don't work any hours, I make $0. But this problem here with the snowfall rate does not include 0, 0. Because at the beginning, there was already 2 inches of snow on the ground. So this value here, which we understand as our y-intercept, takes on a different name right now. Okay, when we talk in functions, we call this the initial value, okay, or the starting value. This would be a good definition to write down in your notes. Okay? This initial value is where the function begins. Just like the phrase states, the initial value. It's the value at the beginning. And you can tell on the graph, that's the same number that typically represents our y-intercept. And you can even look up here on the anchor chart above the smartboard where I identified the y-intercept. I also included initial value because those two terms are interchangeable. Because this is a function and it's representing snowfall and hours, why can we with confidence say that that is the first value in this situation and that we don't have values back here where x is -1 and x is -2? What about this? Why are we certain that this is the first value and that nothing back here is possible.
Because at this point, like
X is 0. Okay, X is 0. But why can't X be negative 1?
Because there's no such thing as no negative snowfall.
Is that the snowfall? Negative 1x? Your explanation is correct, but it's not snowfall. X doesn't represent our snowfall.
There's no negative hours.
Right, I can't really talk about negative hours. Right, negative 1 hour isn't realistic. Right? And you would be correct if our X value was snow. Negative inches of snow does not make sense. Right? This is our initial value. So it's all about the context, but it represents the same thing. It's the value of y when x is 0. In this case, when 0 hours have passed, we have 2 inches of snow on the ground. So this graph also shows our rate of change. That's the ratio of the change between y and x. Okay? The rate of change in this example is 1.5 because every 1 hour that passes, what's happening with our snowfall? Our total snowfall is increasing by 1.5. What other number in this was 1.5? What other number did we identify before as 1.5? When we wrote the equation for this graph, we wrote this. What did we say that 1.5 was? The slope. It represents the same thing. And up here on the anchor chart, you can see that I labeled the slope as other names for it: rise over run, change in y over change in x, and rate of change. Okay, the rate of change is how our relationship is changing, which in the graph is represented by the slope of the line. If we were just talking about snow falling and hours passing, that's not a slope, because the slope specifically refers to the line itself. But what if I just showed that in a table, and I never showed you a graph? You wouldn't refer to it as the slope, you'd refer to it as the rate of change. It's what's happening every hour that passes. They represent the same thing. It's how our relationship is changing over time. So we have our rate of change, which is another name for the slope, because it represents the change in our function over time. We have our initial value, where our function begins, where x is 0, the value for y. Okay? And these are things that we can use to compare functions. If I had 2 different storms, you can tell me the rate of change and the initial value for both storms. Can functions have different initial values and different rates of change? Could a relationship begin at a different value? Could it grow at a different rate? Yeah, I see you nodding your heads. Yes, absolutely. What if today it snowed at 1.5 inches per hour, but then tomorrow we had like a blizzard and it got 5 inches of and we had 5 inches of snow every hour? We'd still have all the snow on the ground from yesterday, so our initial value would probably be higher. And then we would see our rate of change. How would you be able to tell? What would you look at if we had a table, a graph, or an equation? How would you tell if the rate of change and initial value is different in, let's say, 2 graphs? What would you look for specifically?
How much is the snow on the wall?
Like for one,
For one, what value is that going to help you find?
a slope.
The slope. So when I look at any relationship, do I want to look at the value of 1 for my slope?
we want to go for a straight line.
Okay, so let's say we have a straight line like that. How would I identify if there's a different initial value?
How steep the slope is?
Is that initial value?
Rise over run.
What would initial value be? Where would I look?
Y-intercept.
I can look at the y-intercept and find the value that represents my initial value. And if I wanted to find a rate of change in a graph, how would I identify how this relationship is changing? How would I find out how this is changing as time goes on? I can find the slope of the line, absolutely. I can see for every 1 hour that passes, how much has my line grown. And you can see here that these lines are moving in a different way. That's something we're going to identify when we compare. What if I'm in a table, and I had 2 tables, and I wanted to find out if they had different initial values and different rates of change. How would I do that in 2 tables? Where would I find the initial value in a table? What 0? What was it? Yeah, where x is 0. So something like this, I can see that they have different initial values. And how would I find the rate of change in a table?
The y.
Is it just the y?
Like change when it goes from one x to another, and then when it goes like the change of y with the change of
Yeah, the change in y over the change in x. And again, that's how we find the slope. It represents the same thing, the same growth. What if I had an equation? How am I going to identify the initial value and the rate of change in my equation? Based on these equations, could you tell me which one had a greater initial value, which one had a greater rate of change?
Yes.
How? What are you specifically looking for in the equation? The y-intercept values here would tell me the value for x, what my result for y would be. And then how could I find the rate of change? Yeah, the slope here. This value represents how my relationship is changing. Now, when we compare functions, typically you're not going to have 2 equations or 2 tables or 2 graphs. Typically, it's going to be 1 table, 1 graph. 1 equation, 1 table. 1 equation, 1 graph. And you'd have to see in both what values you're looking for and how to actually compare them. Is one greater? Is one smaller? Is one growing faster? Is one growing slower? And those are the questions that we'll start to answer once we get comfortable identifying values. So here we have something you're just going to come up with an answer with the people around you very quickly. Dora opened a savings account and deposited $50. When she gets her paycheck each week, Dora will put $25 into the savings account. First question, what is the initial value of the situation? How do you know? And the second question, what is the rate of change for this situation, and how did you determine that? Talk amongst yourselves for about a minute and see if you can figure out these 2 values. Who wants to share the initial value for this situation? We're going to do an activity where you're going to have whiteboards and you're all going to find initial values. Initial value for Dora's money. Or like, why 50? Yeah, it's how much she started with. It specifically says that she opened a savings account and deposited 50. So from that first sentence, we can assume as soon as she opened the account, she put the money in. Right at the beginning, before any time passed, she had the $50 in there. And then what's the rate of change? What's happening?
It grows as 25 each week.
25 every week, $25, and I'll even put it over 1 week right now, which will help in our next activity. $25 every week. Now, how do we know if we wanted to put this into an equation? What would our equation be? David.
Y equals 25 x plus 50.
Perfect. So the big question here, and this is a mistake that comes up occasionally, why is the 25 with the x and not with, why is the x with the 25 and not with the 50? What is it about the information we were given that tells us the 25 has to be the number with the x, not the 50?
It says paycheck each week.
Oh, wait, let me. This is the key. Each week, Laura will put 25 into the account. That's the key. Each week, meaning over time. In 1 week, it's 25. In the second week, she's going to have put in 50. In the third week, it'll be 75. But we can never forget about the amount she started with, which was the 50. So now let's take it one step further, because eventually we'll get here. That's the equation that represents this situation. Dora opened her account with $50. She's adding in 25 a week. Could you tell me how many weeks it would take her to save $1,000? If I asked you to do something, to fill in a value in this equation to determine how many weeks would it take Dora to save $1,000,
40.
what would you do with this equation? How would you figure out? So what would you replace? If we said how many weeks would it take for Dora to save $1,000?
The Y.
You can replace the Y with $1,000 because that would be our total. And think about the question. My question was how many weeks? We don't know the number of weeks. X represents the number of weeks. So we'd be solving here for X. And you were explaining it. You were saying we can take 50 away from 1,000, just like we would solve an equation, and then divide by 25. Now let's say instead of that, the question was, here's Dora and her situation. After 11 weeks, how much money would she have saved? I want to say Dory so bad, but it's Dora. After 11 weeks, how much money did she have saved? What would I do there? After 11 weeks, how much money would she have saved?
You need to substitute X for 11.
I could replace the number of weeks with 11, and then we could calculate. So that's how we can use the function to answer questions. Okay, very good. So we're going to do a little activity here. I'm actually going to pause the video because this part is all, it's not going to be loud.